Okay, so as far as the rules of sig fig, there are 3 rules. Remember that? If it's not your work, if it's your work, you know you have the instrument, you know to write sig figs. But if somebody else's work, what are the 3 rules? If I see a measured number, how do I know if something's significant? What's rule number 1? Don't even look, just think about it. Yes?
Numbers 1 through 9.
Right, if you're not a 0 and you're in a measurement, you're in. You're in the club. All right, next rule, number 2. Of what? Right, if they're in between numbers that are not zeros, like the cream of Oreo cookie, they're in. And number 3 is the only one you have to pay attention to, really. Who knows number 3? That's the toughest one. Ben?
There's a decimal, and if the numbers following a significant figure,
The numbers following is...
or like the number like after the 0.
Yeah, if you have a 0 that comes after a sig fig, right? Or is he in the club or not? Maybe. If you have a trailing 0 comes after a sig fig, he's in the club, he's in the sig figs, if there was a decimal somewhere in that number. See that? That's the only one you really had to remember like that. Then we did this yesterday, where I had you get your calculator out, and some of you, I don't know why, I know what you did. Some of you cut that off. I didn't ask you to cut it off, but if you were in math class and you multiply these two, you would write something like this down, wouldn't you? And that's what I would do if I was in math class, because I want to get the question right, wouldn't I? But your mentality has to change a little bit. A measured number is not the same as a perfect number. And so you can't tell me, hey, we're trying to find the area of something. There it is. That's the area. Oh, you're a liar. You're a liar if you tell me that's the area, because look how weak one of your measurements were. One of your measurements, it only had 3 sig figs. You're telling me you can tell me the area of 1, 2, 3, 4, 5, 6 sig figs? You're lying. So again, statisticians said, well, what can we do to make it more like truth? They say, well, if you multiply or divide sig figs, then you have to round to what? What's the rule there? It's pretty easy. Round to, Parker, what do you think? Least what?
Sig fig.
List number is sig figs, okay? So this had 3 and this had 4. I'm going to round to 3. If you round to 3, do you ever look at the 4th number? You have to. You don't look at the 5th number, but I look at the 4th, don't I? And it's not big enough. See that? I know that somewhere in elementary school, somebody taught you this. Round that to the nearest whole number. I know somebody has done this. It's wrong. It's wrong. Round to the nearest whole number. Well, that 9 makes that a 10. That makes that a 10. That makes it a 5. That makes that a 3. There is no leapfrog rounding. Somebody taught that. That's wrong. If I say round to the nearest whole number, you're only allowed to look one more place. Now, you don't like that, do you? Because you thought it was kind of neat when you had the leapfrog. No, you can't do that. If you're round to the nearest whole number, this is going to be what? It's 2. And I'll tell you, if you run the prices right, and they said, here, $2.49, is it closer to $2 or $3? If you say 3, you lose. You get it? Everybody got that? Okay, so whatever you have, that leapfrog rounding, and I didn't teach that. All right, so you okay on that? What's the rule when you add or subtract? I wish it would have been the same. I wish it would have been the same rule, but statistician says no, you want to be like truth. So the rule says if you're adding or subtracting, you don't even count sig figs. You don't even count them. It's the least number of decimal places. So we go over here. This is hundredths place, tenths place, ones place. The ones place. So if I were to round to ones place, do I ever look at tenths place? I have to. Not big enough. See that? Also, your calculator does not know what a meter times a meter is. You do. Your calculator does not know what's a milliliter plus a milliliter plus a milliliter. So you have to do that. See that? All right. Now, that's enough review there. You can do some more of those if you want. Now, what I'd like to do is I'm going to give you a ruler. And what I'd like you to do is to try to fill out this chart, okay? So what you're gonna get the wooden rulers again, and remember the wooden rulers have a side that's called A, and the lines are like this far apart. Remember that? It's a decimeter ruler. Then you have another ruler, another side on that piece of wood, which are centimeters, and then you have a real ruler, which will go down to tenths of centimeters on it. So what I'd like you to do is, I want you to measure this and calculate the area and calculate the perimeter, and I'll just walk around and see how you're doing, okay? All right, so let me get the rulers, and we'll do that. If I do the wooden rulers, you guys hand up the other ones? They do make a nice sound. Exactly. All right, so ruler A is one that has only decimeter marks in it. Ruler B is on the piece of wood, it only has centimeter on it. All right, did we run out? Okay, good. All right, I'll walk around the room, and this is a neat mini activity because just at measurements first, okay? I'm gonna walk around, I'm gonna see whether or not you have the right number of sig figs. Then when you do your calculations, you have to stop and think a little bit. So ruler A, this guy right here, ruler A here. And we did this yesterday, I think, but that's fine. It's right here, you're gonna measure less than one. Okay. So you're using 3 different instruments to measure the same objects, and yet and then when you do your calculations, your brain has to start thinking about what do you do when you do calculations with sig figs. Saying, well, let's see, I'm certain about this because I have lines. I don't start to guess until I get to this place. And you have to make sure you have units. If you're in math class, you never put units, but you have to put units on these, right? So let's just say the first number you have 0.7, you have to put 0.7 what? What are the units? Decimeters. I'm going to say, this right here on this rule here. If this was a dollar bill, that's a dollar bill, you have less than a dollar bill. So how many dollars you have? I know, 0.1. 0.7. 0.07. You have 7/10 of a dollar. You guys are thinking about the rules for using calculation of sig figs. price ruler, okay?
What's ruler?
A is the decimeter ruler, this is B, it says it'll be on it.
Oh, I got it.
So this is great practice, you're practicing how many sig figs am I supposed to write, what kind of unit is it? And then when you do the calculations, you have to know the rules for calculating with sig figs. So it puts it all together for you. Oh, this is ruler C here. So ruler A is this one, the decimeter ruler. Ruler D will be on it.
Oh, okay.
So you can just switch the letters if you want. Ruler C is this one here. The wooden ruler has two things on it, has A on it, has decimeters, and has centimeters. But the ruler C is a nice, what, ruler. I'd rather, at this point, you don't have to put it in scientific notation, but you can, and that'll still show me the right number of sig figs. But, you don't have to right now, we're just trying to work on calculating with sig figs. Sure, you don't this way. Let's try to wrap it up in the next minute or so, okay? Are you done, Clayton? Are you done? Okay. Guess everybody stop for a minute. I need to go ahead and move on. Clayton's gonna give me his numbers, and we're gonna look at them, and we wanna see if it looks right to you, okay? So, using ruler A, which is, only has this many marks on it, they're decimeters, so I know they're decimeters. What did you write down for, the length of this thing?
0.6.
All right, 0.6. Now, did anybody else have something different? You have 0.7? Okay, I'm all right with that, because we know there's only one sig fig here, right? And I know it's a guess. You guessed 0.6, they guessed 0.7. I'm okay with that. What do you have for width?
For width, I had 0.8 decimeters.
0.8 decimeters? Anybody have something different? What do you have? 0.9? I'm okay with that. You see that? And I know that in both cases it was less than a decimeter, so you had to guess. So I'm all right with that. You get it? Now, what do you have for the area? What did the calculator tell you it was?
The calculator told me it was 0.48.
Okay? And the calculator doesn't know that these would be square decimeters. So, did you write 0.48?
No.
The rule is when you multiply or divide sig figs, you have to round to the least number of sig figs. 1, 1. If I round to 1, do I ever look at the second one? I have to. So what'd you put down?
I put 0.5 decimeters.
Now I know that kills some of you. You hate that. You hate writing 0.5 instead of 0.48, don't you? Because you know in math class, you better write 0.48. Is that right? You can't. It'd be lying to people to say the area is 0.48. See that? In math class, they have perfect numbers. These are measured numbers, right? Now, what do you do at the perimeter? Their perimeter would be what? What's the calculator say? Do you have that written down, maybe?
I don't have a calculator set now.
Okay, I can do it. 0.16 plus 0.12, 0.28. What'd you get?
2.8 was the rounded.
I mean, 2.8, sorry. 2.8. What's the calculator say? Okay, so we got 1.6 and 1.2. Calculator would say 2.8. Okay, the calculator would say 2.8 in this case. Now, did you write 2.8 here?
I did.
The rule says for adding and subtracting, this is adding, that I need to add this and this and this and this, don't I? But you don't count sig figs when you add or subtract. You count the least number of decimal places. Tens place. Tens place. I have to round to what? I have to round to what? Tens place. So tens place is right here, and I don't have anything after that, so I am allowed to write 2.8. Did everybody get that? All right, thank you. All right, somebody else, I need their numbers for B, ruler B. Tucker, what do you have for the length of ruler B using ruler B?
6.9.
Okay, hang on. 6.99. I'm going to take a look at ruler B, and you certainly can have 1 and 2 and 3 and 4 and 5 and 6. You can have 6. You can be certain about the ones place, can't you? But when do you start guessing?
At the first one.
The tens place, right?
Yeah.
That's as far as you can go. That's as far as you can go. So what made you say 6.99? Because you thought it was really close, didn't you?
Yeah.
But you're not allowed to. You can say 7.0. You can say 7.0, but and I know it's going to kill you because you think it's 6.99, but you're telling me a lie. You're telling me your ruler, you can be certain about tenths place of a centimeter. You can't. So you wouldn't be allowed to write 6.99 on that one. Now, what do you want to have? Do you want to have 6.9 or do you want 7.0? You sure?
Yeah.
You had a 6.99.
Yeah.
Okay. All right. What do you have for this one?
I have 8.9.
Okay. Do you happen to have what the calculator is on this one?
Yeah, but I did it with 6.99, so it was 62.
Okay. Can you do it again and do 6.9 times 8.9?
Uh, 61.
That's what it says. That's all.
No, it's 61.41.
Okay. And the rule is we have to round to what?
2.
The least number of sig figs, 2. All right, so we have to round to the least number of sig figs, that's 2. The 4 is not big enough, right? So I have to put 61.41. That's it. Ever get that? I know you said we don't like this. Calculator gives you that number and you hate it because you can't write that number down. That's so bad. You're living in a world of measured numbers. Okay, what about the last one? Do you happen to have the calculator on that one using 6.9 though? How about do 6.9 plus 6.9 plus 8.9 plus 8.9, or 6.9 times 2 plus 8.9 times 2?
It's 31.6.
How much?
31.6.
6 even?
31.6.
Oh, 31.6?
Yes.
That's it? Nothing else? All right. So now, the rule is, when I add subtract, I don't count sig figs. It's the least number of decimal places. Tens place, tens place, tens place. So in this case, I am allowed to write 31.6 centimeters, right? Is that what you had? All right. Volunteer for the third one. Yes.
So, for width, I had 7.19.
Centimeters?
Yep. And then, that was length, and width is 8.85.
Say it again.
Width is 8.85.
8.85?
Yep.
What's the calculator give you?
For area, 63.6315.
All right, what are you going to write down?
I wrote down 63.6
And why'd you do that?
because that is the least number of sig figs.
Yes, and there are 3 and 3, so I had to round to 3. I look at the fourth one, not big enough. Everybody get this? We're getting pretty good at this, aren't we? All right, what do you have for this one? Calculator.
I had 32.08.
What'd you write down?
I wrote 32.08 because it's 2 decimal places.
All right,
So
hundreds
it's
place,
half the decimal.
hundreds place, so I round to hundreds place. That's right. What do you think? Does that help you? That's pretty good, isn't it? It's, now, even though you did a little bit of this in 10th grade, is this pretty a lot easier now? I think I told you I talked to Michael, or Miss Fallon's talked to her son, and they said they were doing that at UVA freshman chemistry class. That's what they were doing this, and they expected them to know how to do calculations, how to do sig figs, and you guys aren't even ready for college yet. So, oops, there we go. What do you think? There you go. So that one is, we pretty much did that. Now we want to go to this next part. This has to do with some vocabulary words that have to do with measurement. Now we'll get back to, we're going to get back to sig figs in a minute. But anytime you're in a science class that's more of a math-based science class, when colleges say they'd like to see you have three sciences, and one of them should be a lab-based science. What they really mean is you can do a lot of labs in biology. What they really are looking for is more of a math-based science, and that's physics and chemistry. And those are all quantitative. A lot of the labs. Now, I can do a lab in chemistry. It'll say, hey, what color was the precipitate? Yellow. Well, that's just qualitative. You get that? I'm just telling you what it is. It looks yellow to me. So qualitative just tells you it looks yellow. It's there are 3 things in it. Not 3, but it just tells you what it is, what it tastes like, feels like, that kind of there. But as soon as you start putting a measured number on there, it becomes a quantitative situation. So most of the labs in physics are quantitative. Is that an easy word for you now? Quantity, number, quantitative, okay? I remember in college, I had to take a class. I was so naive about so many things. I was not taught. There's a lot of things I wasn't taught, but one of the chemistry classes I had, it was a pretty high-level chemistry class. It says quantitative analysis. I said, I thought I had to take chemistry. And it said, I'm taking quantitative analysis. Well, it was a chemistry class, but we had to do a lot with measurement in chemistry, get it? And how to do with measurement. And we had the instruments, really neat instruments too. Okay, so you okay with those 2 words? Pretty easy. All measurements contain 3 things they have in common. They have a number. Guess what? We just got done talking about the numbers. They're called significant figures. Get it? That's how that fits in. It has a unit. and it has error. Every measured number has error. They actually do have rulers that measure down to near the angstrom level. They're definitely nanometer level. So you didn't measure nanometer level. So even if you were really, really careful with that nice ruler I gave you, it had error, didn't it? Okay, I'm okay with that. Some of you don't like that. I don't like this. I like math. 5 is 5. But it's okay to work. Look, it's okay to work and live in a world where you use measured numbers. You just have another set of rules, a little bit different rules. Okay, remember it's very important to make good, reliable measurements, because you'll find out later in this class you're going to make graphs. You're going to graph your data, and you're going to find maybe the slope. If it's a straight line, you find the slope, and that slope is the number we're looking for. If you have bad data, you have a bad graph, bad slope. Everything's messed up. You get it? I want you to be good at measurement. If you go to college and you take a science class and they ask you to measure something, I want you to be that person that stands out and you actually carefully measure it and you write the right number of sig figs. You get that? And your partner's saying, well, it's about 15. You say, who taught you? All right? You should be taught to measure correctly. All right. We have these two words that are going to come up called precision and accuracy. We're going to talk about those in a minute. We also are going to have some words that go like this. Measurement standards. Standards are something that sounds boring, but they actually rule the world. The whole world is set up against standards. What I think is interesting is how maybe you've never done this, but what is the standard for your life? Are you kidding me? It's what's on TikTok. That's your standard? See, and a lot of people don't understand that. A standard, I don't have a standard for my life. Well, you do. It's the Bible. And yet a lot of people don't like that. No, I want to be able to do this and this and this. And then your life messes up a little bit and you think, well, maybe I should have thought about that a little bit. So you operate on a standard. The science world operates on standards. The economy works on standards. So if it works for everything else, you think, well, not for me. I don't need a standard to live by. Okay, that's up to you, right? You're making that choice, aren't you? Let's go over here. And the word standard is going to come up a lot in this unit. And what I wish somebody would have told me this a long time ago, standard has many, you can say the same thing many ways. And we did this in 10th grade, we'll do it again. How many things mean the same as a standard? What's another way of saying it's the standard? What is it? Standard? It's right here. It's called the what? Help me out. It's right here. Yes?
Accepted value?
The what? Accepted value. It's the accepted value. What else? What do you think? Yes?
True value.
The true value. Next. Is she the only person that's found this on the paper? Yes?
Given value.
It's the given. It's the known. Is that correct? Is that it? And I wish somebody would have told that to me. Here's another one. It's the theoretical. It might be the theoretical value. You see that? There's another one. I wish somebody would have told me they all mean the same thing. Because down here, for example, we're going to use this equation all year. You might as well learn it right now. We're going to use it all year. If we do a lab, I'll say find a percent error. On this test, I'll probably say find a percent error. A student did this and this. And you say, what? How do you do that? Well, it depends on what book you're looking at. Here's one way I found it in a book. The experimental value minus the accepted value divided by the accepted value times 100. Okay, now does that make, let's see if that makes sense to you, okay? What is the accepted value? It's the target, it's the true value, it's the known, it's the standard, get it? It's the accepted value, right? What's this?
What you're trying out.
That's what you got. When you do the experiment, it's the value you got. You get it? So when you subtract these, you're trying to find out how far away from the target, the bullseye, you are. You get that? How far away from the true value are you? And that just tells you your error. But what if I went percent error? I divide it by the accepted value. Everybody get that? Now you'll get a number like 0.35. Well, what is 0.35? Well, guess what this part of it is all about? 0.35 says move the decimal over 2 places. That's what that means, times 100. And 0.35, I hope your math teacher taught this to you, 0.35 is 35%. It is. What's 0.50? What's 1/2? 1 divided by 2. That's 0.50. What's 0.50? That's 50%. Oh, no, nobody ever told me that. See? They're the same thing, aren't they? Okay, so we're going to be talking about this thing right here, and then we're also getting into this word called precision. So what I'm going to do is I'm going to flip this paper over. We'll come back to, there's a couple words I skipped over. I'll come back to those. If you have your calculators, what I like to do is the second equation that I'd like you to learn in this section, it's not too bad, and it looks like this. By the way, percent error is what we use to find accuracy. So if I say find the accuracy of your number, you find the percent error. Now, there's a couple things, though, in science. Accuracy is nice. Accuracy is nice to know. But there's another word called precision. Now, unfortunately, in everyday language, I think humans think they're the same thing. Hey, how accurate was it? What do you mean? Yeah, how precise was it? They're not really the same. Is anybody in this room do anything like shooting at targets? You do? Do you know the difference between accuracy and precision? Okay, could you tell them in your words, not my words, what are your words? Tell when you're shooting at a target.
The difference between accurate and precision is accuracy is how close you are
To what?
To the bullseye, to the center. And then precision is how tight your grouping is.
So
It could be way over here.
So you could have a tight grouping and be very what? Precise, but not very accurate. Could you find the accuracy of one shot? Why not?
You have to have multiple points of data because accuracy is part of the equation, right?
So if I shoot one shot at the target and it hits a bullseye, could you say I was accurate?
Yeah.
Okay, so I can actually find the accuracy of one reading, but can I find the precision of one shot? Precision always is a group, and precision says how close are you to each other. You don't even say the word bullseye on that one. See that? So let's take a look at this. I'm going to use this equation to find precision. Okay, precision. This little sigma means what? Have you ever had that in math class? The sigma sign means the sum of. You add them all together, okay? Sorry. All right, so this means the sum of the deviations divided by the number of measurements. It's called the average deviation. So we're going to do both those today and see how we come up. So if you have a calculator, here's student 1 and here's student 2. All right? Now what I'd like to do is, this person did the experiment 4 times, and so did they. What I want to find out is, what is a fancy word to say? What does mean? What does average mean? What's the mean? What's the mean? I'll put in parentheses. What's the mean? Average. Okay, so how do you find the average? Ready? Add these up and divide by 4. Let's do that. Add these up, divide by 4. Add these up and divide by 4. And when I call on somebody, please give me the right number, okay? Add them up, divide by 4. Are you done already? Wow, that's fast. Okay, Parker, what you got for this one?
73.09 grams.
Say it again.
73.09.
Grams, okay. Did everybody get that? Okay, good. Do the next one.
Yeah, I accidentally cleared it from the site.
Oh, you got the next one?
Yeah,
Alistair?
71.995.
Now, we have a problem here. If I'm in math class, you're right. If I'm measured numbers. Now here's my question to you. When you add these up and you divide it by 4, this is important. You divide by 4, why didn't you have to round to only one sig fig? 4 only, how many sig figs does 4 have? How many sig figs does 4 have? How many? 1? Alistair says 1. What do you think? 1? I think if that's true, then you would have to round that to 1 sig fig. But something doesn't seem right, does it? It doesn't seem right to do that. Yes.
Doesn't 4 have infinite?
What? Why would that be?
Because 4 is just.
It's 4. It's a counted 4, isn't it? It wasn't a measured 4. This has an infinite number of sig figs, doesn't it? Infinite 4. I'm going to round to what? 4 sig figs. Now, ready? Give me your real answer when you round to 4 sig figs.
71.9.
Uh-oh. What is it?
That doesn't sound right.
If I round to 4 sig figs, do I ever look at the next one? Ever? Ever? I have to. And I'm big enough.
72.00.
Oh. Oh. Okay. All right, everybody got that? Okay, now, so we have the average, don't we? Now, the next thing is, what is the true value? You say, I don't know. Well, let's read the paragraph. Student 1, his average is 73.09. His first, blah, 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 okay. Wait, where is it? I had somebody type this one. Wait, where is it?
Yeah, it never tells you the truth.
What?
You say can't
Let me look on the next page. I did on the next page. See, the next page is not typed. Okay. The true value of 73.00. Okay, sorry. They were supposed to write that down here. Okay. So if you didn't know that, if you did not know the true value, you could not find percent error. Is that right? You cannot. But now we have it. We have the bullseye. So how do we do this? And I'll give you a little clue if you don't want to make a mistake. When you have something minus something divided by something, what's the calculator not like? Remember that? Please excuse my dear aunt. What's that called? Order of operations? You wanted to say this minus this divided by that. Because that's the way I see it. But it won't. What will the calculator do? What is it? Does it do subtraction first? So when you say this minus this divided by that, it's going to divide first. You're going to get the wrong answer. So what do you have to do at the top? Parentheses. Let's try it. Ready? 73.09 minus, 73.09 minus 73. What's that give you? 70. See, the experimental value, that's this guy. This is the experimental value. And what's the accepted value? Also known as true value, standard, right? So 73.09 minus 73 in parentheses, right? And then what? Divided by what? 73. Okay, so let's try that. What's the percent error for student 1? Sarah, do you have that? What's the,
Student 1,
how much?
before, do it. You want me to multiply by 100?
Yeah, tell me what you got on the calculator.
0.123.
0.123? Now you already multiplied by 100, right? Okay. Okay, so this person is 0.123% error. Did everybody else get that? Can you check that? I don't want to go any further unless if we're not getting the same number. Okay, now do the same thing over here to this student and find out the percent error of that one. What is percent error for student 2? Do you have it, Walker? What's student 2's percent error?
Negative 1.37%.
1 point what?
37.
Okay. Did everybody else get that? Okay. Now, I'll tell you what's interesting. What's interesting about this? If you look at some books, like the one I wrote in here had absolute value bars, didn't it? That means there really is no such thing as negative error. There's no such thing. Error is error. You have a project you're going to be doing pretty soon here, and you get to do it twice. I had one group, kind of funny, they said, we had negative 5% error one time and positive 5% error next. What's our average? 0. They thought they should get an A+. What do you think? Well, in math, +5 in my... Yeah, that's good logic. No, it's not. What was your error in the first time? 5. What was your error in the second time? 5. What's your average percent error? 5. You thought they were perfect? So, anyway, so let me tell you what that means. Some books don't put absolute value bars because some scientists want to know, I had an error, but negative error means I was under the bullseye by that much, you see? So then, it's not negative error, it's an error under it. And if it's positive, I mean, I overshot the target. You get that? So there's no such thing as positive or negative error unless you want to know if you were over or under the target. So don't worry about the negative, okay? It's still 1.37% error. Did everybody get both these numbers? I don't want to go any further if we're not getting these. So which student is more accurate? The one with the smallest percent error. Ding, 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 ding. Everybody get that? Now, I don't think that one's as hard. I don't think percent error is hard. We're going to use that all year. We'll use it all year, okay? Let's go back to the next equation up here. How do you find out who's more precise? What I want to know is who's got the tighter cluster. That's what you mentioned, right, with shooting? Whose cluster is tightest? And so how do we do that in science? What we do is we find the average deviation. So watch. I got 72.75. What was the average? What was the average? Don't look at the bullseye. Don't look at the bullseye. His average is 7. So do this. Ready? What is 72 point? What is? And don't worry about plus or minus here. Okay. What is 73.09 minus that? What if you subtracted those two numbers? Okay. What's the deviation? How much?
0.34.
Nice. What's the deviation from this one? Ooh, I can almost do this in my head. Is it 26.26? Is that what you got, Jeff? What's the difference between this and this? How much?
0.25.
Oh, 0.25? Sorry, I missed it. And what about this one? Now, this one I know I can do. 0.07? And what's the last one? 0.16? Am I doing that right?
Oh, yeah.
Okay, so now, think about this. This is how much I deviated from my own average, from my own average. So how do you find the average deviation? Add them up, divide by 4. Okay, so let's find out what is the average deviation for student number 1, and then do the same thing over here with student number 2. This is a little easier to find the deviations. Look at that. Woo! I do that one in my head. Woo! Whoa, 0. Woo! Okay. Did everybody get this? I'm going to find how far away were you from your own average. See that? From your own average. I'm not looking at bullseye when I do precision. Just like when you're shooting, Alistair, you would like to hit the target, but we're really looking at how close they are together. So if you're really precise, all you have to do is fix your scope a little bit, or your sight, and then you'll get precision and accuracy, won't you? But if you don't have precision, you're not a very good shooter. If you get the bullseye once and 5 other times are all over the place, that's bad. But if you put 5 close to each other, let's just fix that a little bit. Put them right now. Oh, now you're really good. All right, does anybody, what does this one come out to be? Help me out. MSJ, I haven't called on you yet. What's your average deviation here? You add these up and divide by 4.
I didn't know it's
Okay, so do you know how I got these numbers? How far away was this from the average? How far away? That's the deviations. Don't worry about plus or minus. And then add them up and divide by 4. What'd you get?
Oh, I didn't do that.
Okay. What'd you get, Tucker?
0.205.
Can I tell you something? That's good.
It's point
If-
two.
How much?
Point two.
Is that what you said?
Yeah, that's what I said.
I hate these masks. 0.205? Can I tell you something? That's good. If the answer was somewhere around 73 and your average deviation is only 0.2 grams, man, that is precise, isn't it? You're only 0.2 grams away, your highest and lowest value from your average. That's really precise, but now we go over here. What's this one?
0.01.
Oh, that was really good, but guess what? That's unbelievable. That's unbelievable precision. You get that? Now, if I had an instrument in science and I had this kind of precision, whoo-hoo. And that's what you pay for. You pay for precision. And then you have to figure out how to calibrate your machine so you can also be accurate. That is the science. A lot of the science world is that. If you went out there in the real world and you got a job at a lab, and you would hear these kind of things. We have this, here's a $50,000 piece of equipment, but we have to set it up every morning. What do you mean? Well, we paid for the precision, but we have to set it to a standard. We have to calibrate it so it's accurate and precise. If you're accurate and precise, then you feel pretty good about your data, like that. When you guys later, you'll do experiments like this. And if you get data like this, and you do a best fit line, and your best fit line almost touches everything, you're pretty good at measuring. You get that? Here's another group though. Their best fit line goes like this. Now that makes you a little nervous. You got the same best fit line, but guess what? I don't somehow there's something about this one. All right. Anyway, this right here, this is the same thing, just typed. And real quickly, even college textbooks show this. Show an example of something that has no precision and no accuracy. Boing, boing, boing. Okay. You throw 3 darts and they go there. Man, you're not accurate and you're not precise. Show me precision with no accuracy. Boing, boing, boing. Now that's a good thrower. This is a good dart thrower. They're doing something, they got to adjust a little bit. Make some little adjustments. Get that? Boing, boing, boing. See? That's it. All right. Anyway, thank you very much. You had a good class.